In this video, I will be presenting our work titled Semi-supervised learning from demonstration through program synthesis, an inspection robot case study. Our motivation is to deploy autonomous robots in hazardous environments, like mines, oil platforms in the middle of the sea, or industrial compounds where extreme environmental variables can put humans and robots in danger. Robots able to perform in such environment have to quickly respond to emergencies, keep a vital part of the system running when a change in the environment has occurred, so operators should be able to rapidly program them. We can achieve these objectives with learning from demonstration, where an expert user or operator demonstrates the task to the robot for it to perform autonomously. Other useful features in LFD is that no programming expertise is needed by the operator, and that from a single demonstration we can learn different levels of abstractions, for example at the motor command level or high-level behaviors as a combination of low-level tasks. If we have enough data from the demonstrations, we can use deep learning method to train neural network models with the demonstrations. In this case, we will expect high performance, for example, in a model that predicts the robot behavior that was demonstrated by the operator. Also, we expect some degree of generalization, as these methods usually learn features from the training data. On the negative side, the complexity of such models do not allow us to interpret them easily, and they are hard to modify. In this case, if the system is unscrutable, the reconfiguration that we achieve from LFD loses the point. The design goals for our systems are interpretability, flexibility, and explainability. For this, we propose a system that combines semi-supervised learning and sequential importance sampling methods. Our system is capable to induce programs and synthesize new behavior from the demonstrations, and we can have an explainable autonomous model predictive control. Here we present the architecture of our system. The green boxes represent model of data to be used by the system. On the left, we represent the collection of data from the demonstrations. The operator, through an immersive teleoperation mode, controls the robot through a joystick and checks the state of the robot via sensors like cameras attached to the robot. We record the operator actions and data collected from both proprioceptive and exteroceptive sensors. The other given model is an object detector. The yellow box represents where our system processes the data collected from the demonstration in a semi-supervised learning way. First, using unsupervised learning, we are able to infer goals in the demonstration. With the goals, now we can divide the demonstration where a new goal starts. And more importantly, we can label each step of the demonstration as belonging to the actual goal for every time step of the demonstration. With this labeling, we can use supervised learning to train both behavioral models that predicts the behavior demonstrated by the operator. The red boxes are the output of the system. In the middle, we have a model that turns the sequences of goals into a source code that represents the demonstration. On the left, we use sensitivity and counterfactual analysis on the behavioral model so we can have a better understanding of why the robot is taking one decision or another. Finally, we can run the program to repeat the demonstration, or we can modify the program to synthesize new behavior that is run autonomously by the explainable controller. We use a sequential importance sampling algorithm with attribution prior. First, we assume that the demonstration can be represented as a sequence of proportional controllers. For example, in the experiment that I will show you next, the state of the robot is its 2D position and the goal is a position in the scenario. In order to find these controllers, we randomly initialize n particles, and for each step of the demonstration, we loop through two subsets of particles. First, on a subset of the particles, we draw the next goal and controller gains particles from a normal distribution centered in the previous particle with a user-defined variance, thus effectively adding exploration jitter to the particles. Then we evaluate the likelihood of the proportional controller based on the actual state and the proposed particles. In the other loop, for the rest of the particles, we sample the goals and attribution prior that includes desirable characteristic of the goals. I will explain in detail the attribution prior in the next slide. The rest of the loop is the same as the previous one. After this evaluation, we refresh the particle samples by drawing n samples from the likelihood estimation. The attribution prior phi is based on two functions. The first one is the pixel sensitivity of the goal in a visually grounded neural network that predicts future behavior. In this case, we train a convolutional neural network that predicts the future states of the robot based on an image of the scene and the actual state of the robot. We translate the goals to pixel positions on the image and calculate its sensitivity to the output based on gradient localization. The other likelihood function represents the distance of the goal to the actual demonstration. We use effective particle size to identify the chain of proportional controllers in a demonstration sequence. When most of the particles have lower probability mass, a clear controller is undecided and happens at the beginning of a path that is characterized by a low effective particle size. When one particle accumulates most of the probability mass, a clear controller has been found, which usually happens midway between goals. In this case, there is a large effective particle size. We use a peak detector to find these points and cluster them with an elbow criterion k-means algorithm to find the sequence of controllers. Our experimental setup is a surveillance task of a Husky robot on an oil platform digital twin. The operator has access to onboard and top view cameras. In the top view image, there is a tower that the robot cannot traverse. And on the sides, there are holes with different obstacle configuration for different demonstrations. The task is to drive the robot from area number 1 to 2, 3, 4, and 1 again, then returning through the same path to the first position. We ask the operator to repeat the task once. The bottom images show the distribution of gold particles in the scenario during the processing of the demonstration, the effective particle size, and the centroid among them shown as the red dot. Here we present the results for two demonstrations with the same task but with different obstacle configuration. In the first scenario, there are no extra obstacles, while in the second, the dark red circle are cones in the way of the robot. The white dots are the goals of the proportional controllers. The red dots in the corners are part of these goals but have been filtered by the prior presented before. After the filtering and clustering them, we obtain the sequence of goals and controllers that represents the demonstration. In this case, each color of this graph represents one controller, and you can see how it shows that the robot starts at 1, then 2, 3, 4, then 1, and returns through goal 4, 3, 2, 1, and the sequence is repeated as we ask the operator. With the sequence, we search for loops and palindromes to build a program that will replay the sequence back. This induced program, in this case of 30 lines in Python language, is an interpretation of the full demo that can be understood by a user with programming knowledge directly, without looking at the full demonstration. Now that we have a program of the demonstration, we would like to use it to play the behavior back. If we use the inferred proportional controllers, we will quickly find that they do not generalize to other scenarios where the obstacles are in different positions than the original demonstration. We propose to use a deep neural network for model predictive control. We can label each time step of the demonstration with the goals that we previously inferred. All the time steps are labeled with the origin and destination goal. With this labeling, we can train different models for each goal pair. The model learns to predict the behavior of the robot from the demonstration for the next 10 seconds. Now we use local information for the prediction. There is no need to know what is happening between goal 3 and 4 if we are learning the behavior between goal 1 and 2. This allows us to use different demonstrations that share the same goals, thus adding to the generalization by having one model that can respond to combination of previous scenarios. In this case, we use a similar architecture as for the sensitivity prior, but now the input image is actually centered on the robot. We still concatenate the robot's pose after the feature extraction by the convolutional layer. Here, we see an extract of a demonstration. The operator drives the robot with a joystick and receives feedback from the camera. The task is indicated by the lower right image. After recording, we induce the program and learn the controllers. Here, the robot is autonomously driving through the scenario. The red square is the actual goal and the yellow one is the previous one. After the controller initialization, where the robot is driven to the initial position of the controller, the robot follows the model predictive controller. In this case, they are the yellow dots, until the sequence is complete. Here we compare the behavior of the robot if it follows the proportional controllers and the model predictive control. After training, shown in the first and second image, we replay the behavior on the same scenario. In the third and fourth image, we can see that the proportional controllers are not able to finish the cycle, while the NPC on the red dot finds its way, even in the unseen scenario shown in the last image. By modifying the induced program, we can synthesize new behavior. For example, we can add more repetitions of sequences or combine new order of controllers, only keeping in mind that the end goal of a controller has to be the same as the initial goal of the next controller. Also, we can use other programming control flow techniques like conditionals. In this case, we have added a conditional on the time of execution. This program represents the behavior of the robot going from goal 1 to 2, then 3. If the timer is larger than a set threshold, the robot continues to area 4. Otherwise, it returns to 2 and 1. This program can now be modified to convey complex behavior that is not present on the original demonstration. The image shows a snapshot of the position of the robot. You can see that it moved from 1 to 2, then to 3. And since the threshold was not met, it returned to 2. We only plot a few steps after the robot turned back for clarity. In the last part of our system, we use saliency analysis and object detection as explanation of the behavior of the robot. In this case, we use causal sensitivity analysis to come up with a heat map of the most salient pixels in the model predictive control. Then we use object detection to associate these regions with objects and filter them with the objects inside the onboard camera. The results on the bottom right animation is a representation of the objects that the controller uses to make the behavior prediction. Finally, we use this powerful predictive model for counterfactual explanation. In this case, the robot fails to move across the hole as there is a green barrier in front of it. An operator can modify the scene at the pixel level and pass it through the model to find a configuration that is compatible with the desired behavior. This use case is especially useful when modifications in the real environment are costly or dangerous. In this case, the robot predicts the outcome of the proposed modification, and after that it can be carried out in a real scenario. We presented a system able to induce programs from demonstration, synthesize new behaviors, learn controllers from demonstration, explain the behavior of the robot based on sensitivity analysis, all of this in a surveillance scenario on an oil-platform digital twin. We met our design goals of interpretability by induced program and the high goal-level inference, flexibility by behavioral synthesis and control generalization, and explainability, including interpretability, and by the sensitivity analysis and counterfactuals.